So thank you very much. First of all, it's lovely to meet you. I've been very curious about your group for a very long time. I was hoping I was going to visit. Of course, this is not an option, but at least we can meet in some way. I'm currently a research fellow at the ICG, from which many people have come and gone from your group to the ICG and vice versa. And today I will talk about Vainshtein screening and whether it's theoretically viable. So Vainshtein screening is a type of screening, which means a reduction in a fifth fundamental force, and this can occur in several dark energy models. Don't worry, I'm going to explain this much better. This is the problem we're dealing with and why. It is a general feature of theories that try to explain the cosmological constant problem, that try to explain why it has such a ridiculous value to come with extra scalar fields. Now, the point is, whenever you've got one extra scalar field, you've also introduced the mediator of an extra fundamental force. You can't have one without the other. So then one question you can already ask yourself is, do we see any extra forces experimentally? Because several models of dark energy write out dark energy as an extra scalar field. So this is already something you can ask yourself. And this is also where the particle physics point of view of putting in an extra scalar field to try to understand how the cosmological constant problem works goes well with the dark energy part. Now, as to whether we see any extra scalar forces, the first answer you can give is a resounding no. So what I'm showing you here is what happens in Earth-based experiments on the left and solar system experiments on the right, when you allow for an extra fifth fundamental force with a finite range to exist in addition to the Newton force. So I'm showing you here a potential where you've got a coupling strength. So this is how strongly your extra force interacts with matter. So for instance, if the coupling is 0, it doesn't matter how much of a scalar field it has, it will not see matter, it will not do anything. So this alpha parameter is how strongly your extra scalar field interacts with matter. This lambda parameter is the range of your fifth force. So in particle physics, whenever you've got a scalar field with a mass, the more massive it is and the shorter the range of the fifth force is, and vice versa, the less massive it is and the larger the range. So for instance, the photon has 0 mass, so electromagnetism under normal condition has infinite range. And so goes gravity. But for instance, the weak force instead has massive mediator, so the range is finite. So in this case, the field, for instance, has a mass, and so the range is finite. Now, what does this? Essentially exclusion plots. You are excluding regions based on the coupling strength and the range of a fifth force. And both on Earth and in space, we see absolutely nothing. And this you can keep updating in more recent years with more and more experiments still doing this. So then you could say, okay, I think this is slide 3. It's already finished at slide 3. Actually, no, because what you're really excluding here is just the simplest possible model. So what you're really excluding here is what in the particle physics language is called a canonical scalar field with a small mass. So simplest possible model, and in particular, a linear theory. So you may ask, what's wrong with this? Are these the theorists who are doing everything in their power to avoid my later constraints? I don't like that. Actually, not necessarily, because to start with, the one scalar field that we know that exists, which is the Higgs boson, does not behave in this way. So for instance, in this way, you don't cater for the one scalar field that we know that exists. The Higgs doesn't behave this way. And also from a particle physics point of view, in some sense, you need to know why you need to restrict this, because this is a linear theory. And why don't you have nonlinear interactions, for instance? There is not necessarily a reason. If you have a reason, that's fantastic. But without the reason, it's a bit difficult to know why that would be the case. I know that observationally, the story is different, but and it's completely fine. I mean, the observational story completely makes sense. But from a particle physics point of view, this is really not clear. So then, if you go and look at a more general model, it turns out that if your scalar field has non-trivial self-interactions, like the Higgs does, for instance, then your fifth force may have a more complicated behavior. And the key thing here is that it can become environment dependent. So whether your fifth force is strong or weak or whatever will depend on what's happening around. And in particular, it can be screened, which means suppressed, in some environments where we know that it has to be small. Okay, this is the key thing. However, you don't just want your scalar field to hide and do nothing. Otherwise, what's the point of having something that doesn't exist? The idea is that you might still be able to see it on cosmological scales, where it can still be useful and mediate a long-range force. Okay, you don't need to speak Lagrangians if you don't. All you need to know is that this is a more complicated model that allows for non-trivial interaction of the field with itself. So then, in terms of what I was showing you earlier, which was a potential of this, in addition to the Newton force, you've got this extra force, and this is the potential, so some coupling to matter, some finite range. And here a mass is a source mass. What happens here is that some of these quantities become environment dependent. So for instance, maybe it's your coupling to matter that depends on the environment, or maybe it's the range of your fifth force that depends on the environment, or maybe it's not just a dependence with a source mass that's trivial. You don't just have a linear dependence. Perhaps it's more complicated. So for instance, in several models of screening, what matters is just a thin shell around the source radius that matters, not all of the mass. Okay, so this is an example of how it works so-called in real life. So you may think this is really contrived, but actually one of the forces we know and love, which is electromagnetism, does something like this, does something really similar. So this is the Debye screening of electromagnetism. Imagine you've got a plasma of charged particle. Now you look at one of these charged particles, and it turns out that its influence is only felt up to a Debye length. And this Debye length you can phrase in natural units in terms of a Debye mass, which is a function of several things, including the plasma temperature and the electron density. Now you can phrase this thing as being due to the photon having acquired a mass because there was this charged plasma. So you can phrase it as the photon having acquired a mass based on the environment. Okay, so this is not something weird. This already happens with the forces we know and love. Right, and this is an example of again what can happen in a case that's relevant to dark energy. I will not specifically talk about this, and this model actually has problems with UV completion, but it's useful for what I need to talk. And I will admit I always show the slides because it allows me to show a chameleon. Come on, who doesn't love a chameleon? So anyway, what happens in this case? The chameleon mimics is a model of a scalar field for dark energy where the mass mimics what's going on in the environment. So if the density is high, like in the center of a galaxy, then the mass of a chameleon is large, and then large mass means short range. And instead, in the outskirts of the galaxy, where the density is low, the chameleon becomes small mass and long range. Clearly here, we are talking of effective quantities. We're not talking about the fundamental mass of a field. We're talking in terms of effective potentials and how things play out, okay? So this is one example that you may have heard about a lot if you work in dark energy. This time, though, I'm going to focus on another screening mechanism that is called Vainshtein screening. So this is quite different. Vainshtein screening, turned up, for instance, in theories of massive gravity. This is why you may have heard of it. It works in a very different way. In this case, it's like you have different laws governing your fifth force depending on the environment. So rather than being the mass or the coupling, in this case, I mean, it's related to the coupling, okay. But in this case, what happens is that it's like your fifth force follows one law in a certain environment and different law in a different environment. And here is an example of how that may happen. I'm showing on top for comparison standard gravity. So this is the Poisson equation. Even though it may not look like it, this is the one you solve in M-body simulations. And below, I'm showing you one of the simplest models displaying Vainshtein screening. It's called the cubic Galilean. Here, in this equation, I've highlighted some terms in aquamarine. I like saying the words aquamarine, and some terms in white. The white terms are the standard ones, and then you've got the aquamarine terms, which are discomplicated non-standard terms. Now you can show, because this theory, even though it looks complicated, fortunately can be integrated analytically. So you can actually solve the behavior if you've got a static and spherically symmetric configuration. And so it turns out for a spherical and static source, closer to the source and up to some Vainshtein radius, you've got that these non-standard terms dominate. And instead, further away from the source, you recover the standard terms. So it's like closer to the source, you've got a force law that's governed by these non-standard terms, and further away, it's governed by the standard terms. And because you can integrate this analytically, it turns out that closer to the source, your force scales like the radius to the 2/3. So this is weaker than gravity. And away from the source, it scales like gravity. So like 1/r², right? And the catch is that typically this Weinstein radius is huge. So for instance, if you were trying to do lab experiments like you do for other models like the Chameleon, Symmetron, Dilaton, blah, blah, you couldn't do this because even if there were no Earth, your lab would be screened by the galaxy. So, you know, the Weinstein radius is so huge that, you know, you're screened really by, it's really, really effective, basically, which also made it a bit more difficult to test compared to other mechanisms. And as you can see, also the fact that equations are quite horrible and complicated made it a bit more difficult even to understand what's going on sometimes. Here is where our work comes in. And it is that this description is really interesting, really effective, but there is a problem at the theoretical level. So even before you go and look at observational constraints, there is some theoretical problem here. The theoretical problem is the following. Typically, these theories with Weinstein screening have a very small limit of validity compared to general relativity. So some of them, for instance, can break at kilometer scale. This is bad because, for instance, it's unclear that you can do gravitational waves with these theories. People typically say, okay, this is not a problem because you don't need this theory with Weinstein screening to be the actual fundamental force governing your fifth force. All you need is that it's the effective low energy theory of something else. So if your theory with Weinstein screening can be extended to a more fundamental UV complete theory, or even to a more fundamental theory that holds at much larger energy scales, this is completely fine. So for those who don't speak this language, UV completion is the process by which you extend a low energy theory to a theory that's valid at higher energy scales, even, you know, or even being, you know, UV complete means complete in the ultraviolet, so really, really small. Yeah, so the question is, if you've got a UV complete theory that you can extend your theory to, this is fine. However, there is a problem here with this reasoning, because if you say, on the one hand, my theory with Weinstein screening is the low energy limit of a more fundamental theory, you're putting yourself in a perturbative regime. Your mind is in a perturbative regime. But at the same time, you're saying, yes, but my non-standard terms are dominant and macroscopic. This is not a perturbative thinking. So if you think like when you do even perturbation theory in terms of the density field, you know, if your nonlinear terms are much, much, much more important than the linear term, well, maybe your perturbative approach has broken down. Maybe you can't do, you know, think in a perturbative way anymore. You can't, for instance, use, just perturbation theory for a black hole and stop at linear order, because the thing has broke down altogether. So then this is unclear. You've got something macroscopic, but perturbative. And then the question is, if you know that this particular complicated term you can write down is macroscopic, how come can't you write down other terms, non-standard, that are also macroscopic? And the reason why this is important is that how do you know that these terms don't cancel out? Because essentially you're saying that Weinstein screening relies on these terms to be important and to be there, but maybe if this is big, other terms are big and destroy this behavior. How do you know? And the truth is that you don't. You only really know if you know the full UV sector, which means you know this full giant fundamental theory that is the real theory behind your low energy theory. And therefore, because you know you've got this super knowledge, you can know that this term is important, but others aren't because of the way the theory behaves. And so you know that everything is fine. So this is then a more general picture. So you've got classical linearities, classical non-linearities, and quantum. And then this is the theory suspicion here. you can think of these theories of massive Galileans, so scalar field with a mass that have this behavior, or this Vainshtein behavior. You can think about two classes of theories. There are the so-called lambda-3 theories, where you expect that your quantum corrections behave. So you expect that your nonlinearities that are classical will kick in before your quantum behavior becomes important. However, the one way we know of UV completing theories is not possible. So how do you UV complete theories usually? Usually you bring in an extra particle that takes in the infinities you don't like. So typically the problem with UV completion is that as you go to smaller and smaller scales, you've got infinities that pop up and that you know shouldn't be there. However, and this is for instance the way supersymmetry works, sometimes you can put in an extra particle with a higher mass, and this extra particle will take away all of these infinities. And so the infinities will go away, your theory becomes to be complete. Now you can prove that this is not possible in this class of theories. So this behaves, but the standard way of view completing is not possible. Maybe there are other ways, but then I'm saying, okay, give me one of these ways and show me screens. Because currently the one way we know of you completing things does not work. And then you've got the different classes of theories, and here we know that we can UV complete in the way we know, in the normal way. However, this suspicion is precisely that your quantum corrections will become important before your classical linearities do, and there is no Weinstein screening. So then, in some sense, the suspicion is that there is a small cover. Maybe this is not true, because maybe in the other case, you can build a different kind of UV completion. But currently, with the state of things, this is not clear. So then, this is where we come. We would like to have, for the theories where at least it's possible to UV complete in a way we know, we would like to take a UV complete theory and make this experiment, but it's a theoretical experiment. So take a UV complete theory, take its low energy limit, and see if the screening only exists at low energy or if it survives the extension to the UV complete theory. Now, UV complete theories aren't exactly easy to come by, because then you could ask, why hasn't this done ages ago? Well, UV complete theories, you don't exactly buy them at the shop. They are difficult to make. However, we've been lucky because a few years ago, these people published this A theory that's UV complete, and it's a theory of massive Galilean actually. And in this case, you've got exactly this way of UV completing by putting in a more massive scalar field. So you've got a light field, that's this phi, a more massive scalar field, that's this h, and you've got some complicated behavior there. You can show that this is a theory of Galileans, even though it may not look like it to those of you that do modified gravity. So a bit more complicated equations, but it's a UV complete theory of massive Galileans. So does it screen? So these are the equations of motion. It means the equation that regulate the behavior of your field. And what you're really interested in is the behavior of your lighter field. The more massive field will kick in at higher energy, okay? And as you can see, imagine you want to do embodied simulations with this. It's quite horrible already because the fields are coupled and there are no linearities. This is already nasty. But the question is, does it screen? And then you can look at the lower energy theories that you can create from this and look at the perturbative approach. So build the tower of operators, of higher and higher order operators, and you can see whether this series converge. So to make the link with what you do in perturbations theory with the density field, you can look at the tower of higher and higher order terms of the density field, and you can see whether the thing converges in the first place, which is another way of saying whether the perturbative approach was appropriate in the first place. And if the theory converges, then yes, otherwise no. And there is something to say here. From the particle physics point of view, this is not exactly the same as taking the low energy limits. In a good particle physics point of view, you would integrate out at the level of the Lagrangian the more massive scalar field and make your theory there. This is not what we do in cosmology, though. So we actually do things as we do them in cosmology. The way this is done in cosmology is you take this more massive scalar field and you essentially substitute this term here. And this is where you obtain these towers of operator. Now, the question is, if the perturbative approach works, this is all fine and you obtain exactly the same thing. But you're relying on the perturbative approach to work. So even if you don't speak Lagrangians, what this means If the perturbative approach works, then everything is fine and your Weinstein screening is there. Otherwise, no. So a related question is that also, does it look anything like the high energy theory? Because if your perturbative approach works, then first order is more important than second order, and you're just truncating, and this is fine. If the perturbative approach doesn't work, this has all collapsed long ago. So then, this is exactly what we do. Even if the theory is horrible, we want to solve it. We want to solve it numerically and see how it behaves. And then this is the point. Let's compute the scalar force for the high energy and the low energy theory. Let's see which, if any, displays Weinstein screening. Let's compute the horrible tower of painful operators, comments mine, to see if the series converges. This is exactly what we're going to do. Right, so as I was saying, yeah, we want to do this, but the equations are horrible and the operators even more. And this is where those of you who do simulations may be interested. Essentially, we are down to the familiar problems of physicists that we have the spherical cow and reality, and the spherical cow may be our favorite physical model, but it's not like things are. In this case, it means complex equation, large nonlinearities, all the things are right here. We are going to address this, and we're going to do so by using the finite element method. So this is a method I really like. And we do the simulations using this. To be clear, we still stay in the static and spherically symmetric case, also that we can compare with the analytic understanding, that otherwise is not possible. But because the equations are so horrible, you still need some sophisticated method to go to it. And this is what I'm going to talk about right now. We've developed our own code based on the finite element method, and it builds on a finite element library that it's called Phoenix to do essentially all that I've said we were going to do. And the really tricky business has been computing the operators, where you've got a box, so Laplacian for the static case, the Laplacian of a Laplacian to some high power. Those that do numerics know that derivatives are noisy. Second derivatives are already nasty. If you go to fourth derivatives or something to the power, yeah, that's bad. So this is where much of the sophistication comes in. Right, so how does the finite element method work? The idea for numerical solvers in general of partial differential equation is that the first step is that you must turn something that's continuous and infinite into something that's discrete and finite. In a computer, you can't solve a continuous infinite mean. You have to discretize. And where some of the methods differ is in how you can do this. So one key advantage of the finite element method is that your discretization doesn't need to be uniform. So this is one key difference from the finite differencing technique that I usually employed. So in this case, this is a particularly contrived example where you've got a finite domain where the shape of the dolphin has been carved into a square. And then as you can see, the advantage though is that you can put your discretization where you need it, where you expect large variations. So you discretize the domain, it doesn't need to be regular. Then you discretize your functions. So your field profiles and all its derivatives are functions. So this is what you want to solve. Your solution, for instance, is the function here. And you express it in terms of a finite dimensional vector space, for those who use this language, the finite dimensional function space in particular. So you will have basis functions. And for concreteness, you can imagine that they're polynomials and then some coefficients, right? So we actually use Lagrange polynomials for this, but it's not necessary. You can use whatever functions, well, not whatever actually, but you can use other functions, okay? You can have other choices. So what you will use this expansion for is the function space within one of these cells. So this doesn't mean that your function is a polynomial. It just means that within mesh points where you will try to recover the actual value of the function, you will interpolate in terms of, for instance, polynomials, right? So in this case, I've used triangles, and in this particular case of this particular picture, they're actually linear triangles. So in this case, I'm even just expanding up to order 1, and then I've built a piecewise linear function. But as you can see, because of the discretization, you can have complicated behavior. In the work, we don't use linear functions because, of course, we couldn't. The behavior is very nonlinear, and you've got higher order derivatives, I mean, especially for the derivatives, not because it's nonlinear. But this is to give you an illustration. Step 2. You turn the original form of the equation, which is called the strong form, into its weak form. And to illustrate what this means, I'm going to start from the hello world example of partial differential equations, which is the Poisson equation. Gravity behaves this way, okay? So what does the hello world problem look like? You've got your Poisson equation, and then you've got boundary conditions. The boundary conditions are called Dirichlet when you specify the value of the function in some part of the domain, and they're called Neumann when you specify the gradient of the function in some part of the domain. So this is the complete problem. Differential equation, boundary condition. Now, in the weak formulation, instead of asking that your solution is true, it satisfies the equation in an absolute way, what you're asking is that the equation is satisfied with respect to a set of test functions, but all of them. One of the reasons why this is useful is that if your source is not even a function, it can be a distribution. So for instance, if it is a step function, if it is a delta function, they're called functions, but they're really distributions, these are not functions, then this thing makes sense anyway. Whereas sometimes in the strong form, it's not even clear. Some things may even be badly formulated. So this is a weaker condition than a strong form, of course, but it's useful. So in the weak form, you ask that the equation holds with respect to a set of test functions, okay? And your scalar, and essentially means that you take the scalar product with respect to all of these test functions. So left-hand term, right-hand side term, you take the scalar product with respect to this test function, you ask that this is valid for all of them. And with functions, a good scalar product comes typically in terms of integral. It doesn't have to, but it's useful. We use the Euclidean scalar product, which is also an integral. Why are integrals good? Well, to start with, integrals reduce the order of your derivatives, and derivatives are bad. So this is already nice. There's another reason why integrals are useful, and it is that you can express the second order term by integrating by parts in terms of a boundary term, and you've got this other term. But the useful thing is the boundary term you can express in terms of the Neumann boundary conditions, which means you don't need to enforce them by hand. They go already inside the formulation of your equation. So this is one less thing to do, one difficult thing to do, which is enforcing your boundary condition. This can sometimes be non-trivial. In this case, it's automatic because it's in the way you express your equation. Okay, so what are you left with? You're left with something that's amazing, even if it may not be obvious at this stage. On the left-hand side, we've got a bilinear form of your solution and a test function. On the right-hand side, you've got a linear form of your test function. Why is this amazing? Well, if you remember, the cool thing about this bilinear and linear thing is the moment they are defined on a basis, they're defined everywhere. And we said we were going to expand functions in terms of basis functions and some coefficients. So if you work through the math of these things, it means that essentially the coefficients, you can pull them out and you're left with a bilinear form evaluated on a basis that you chose prior. And okay, maybe this is not yet obviously why this is amazing, because this is a matrix. This is exactly what a matrix is, and this is exactly what a vector is. So even if it doesn't look like it, this has turned into an algebraic system. Matrix times vector of the unknowns equal vector. This is exactly the algebraic system you solve in high school, even though it may not look like it. So maybe this is horrible, but this is a method by which you have converted a difficult partial differential equation into something really easy. Because what you're really solving for is the coefficients of your solution in terms of the discretized basis. So the only remaining step is precisely what happens with nonlinear equations. And then basically the problem becomes a giant root finding exercise. So like when you try to solve, to find the root of a polynomial, you need to use a nonlinear solver. In this case, we use the Newton's method. And this is similar. So it's not exactly the same thing, but I'm not going to give you the technicalities. But it's similar to the Newton method that you use to find roots, except it's a giant root finding exercise because you've got a function. So you're not just trying to find one value, you want to find many. But in this case, then the exercise of solving, a linear system happens more than once because you iterate until convergence. And then you find the solution to the original nonlinear equation through a succession of linear equations. Okay, so pretty pictures here, okay? So the technical part has finished. I am close to giving you the results, but I will not just now because first I want to do advertisement. So in order to show you why this is a good idea, I have deliberately picked an example that is difficult. So for the UV complete theories, I've picked two values of the masses that are hard. So one over the mass is called the Compton wavelength, and it gives you an idea of the range over which the field is interacting. In this case, for the light field, I've picked a Compton wavelength that just 10 times your source radius. And for the heavy field, a Compton wavelength that just 10 times the source radius. Sorry, no, 1/10 of the source radius. So it's inside and 1/10 of the source radius, and the light field is 10 times and outside of the source radius. The reason why this is difficult is that all the scales are really similar and quite degenerate, and you can expect troubles. Okay. Now it turns out, for those of you who are familiar with particle physics, the both of the light and heavy field are not the eigenstates of the linear operator. This means that you expect some excitation. It's like when if you think of the neutrinos oscillations, you sort of have something similar here, which means that the two field mix. Okay, so I'm simplifying things, but it's to give you an idea. What this means is that you expect excitation in the heavy field due to the source vacuum transition. So in this case, on the left, I'm showing a profile that's not exactly a step function, it's similar, and it's having a transition that's more or less steep. And on the right, I'm showing what happens to this excitation in the heavy field. So to be clear, this is not new physics, but it's difficult physics. In order to enforce the boundary conditions at infinity, the Dirichlet boundary conditions accurately, I'm using, in this case, a box that's 10 to the 9 the source radius. And yet we can solve for these tiny features around the source radius. So yes, this is advertisement, but allow me, right? The reason why we can solve for these tiny features around the source radius is precisely because you can put the mesh points where they're useful. And when you expect that the function behaves, you just put a few. If you try to do this with finite differencing technique, with a uniform grid, you will need a huge computational power if you were to solve for the entire mesh with tiny, tiny, tiny mesh spacing between the different points in the grid. And then here, so this is more interesting for the theories, but you may have noticed that our equations were complicated, and understanding what's going on and which terms in the equation dominate is actually quite difficult. I'm not going to explain why, but this is related to the question of whether the theory screens or not. And so in this case, I'm also showing for varying values of the heavy field, which terms dominate. And as you can see on the right, especially for the heavy field, you've got a different interplay of things. And this is the best. Remember the operators, they are really horrible. So in this case, I'm showing an example where I'm computing the Laplacian over Laplacian to the power of 7. This is hard. And yet we can solve for the full behavior of the theory, including several sub-regimes. So the regime where the light field dominates, which is most, the regime where the heavy field dominates, which is this tiny region here, and also different sub-regimes. So the theory is horrible, the operators even more, but we can actually solve for this thing accurately across all of these regimes. So this is nice. Okay, so unfortunately, some people already had to leave, so I'm going to speed up, okay? But the results have come, okay? So to be honest with you, when I started this project, I didn't think we were going to get to this point, but we did, so allow me to brag. Right, so after all this talk, some results. What happens, Weinstein screening and UV completion. So does the high energy theory screen? Do the low and high energy theories look anything like each other? And the answer is no. The low and high energy theory look nothing like each other. What I'm showing here is the ratio of your scalar force and your Fifth force as predicted by the two theories. In the UV complete theory, you see no screening. In the infrared theory, in the low energy theory, you see huge Weinstein screening, where your scalar force is suppressed up to 10 to the minus 8 times the gravitational force. And it looks like the scale at which your theory is breaking down is precisely around the Weinstein radius. So you've got that this Weinstein radius is simultaneously the place where you want your classical nonlinearities to dominate and where you want your screen to start and to make your theory observationally compelling, but it looks like it's also the place where your theory is breaking down. And in terms of the tower of operators, I'm showing you here the first four orders of operators, okay? And what's happening is that the second order is more important than the first, the third and the second, the fourth and the third, and so on. This means the perturbative approach has broken down. This doesn't necessarily mean that the series is diverging, but it means that the perturbative approach has broken down. A perturbative approach is not appropriate here, which again gives you the same idea. It's unclear that you can actually invoke Weinstein screening within the limit of validity of the theory that uses it. And this goes to my summary and conclusions. Weinstein screening is an effective mechanism to hide the fifth force in high density regions, or high curvature regions actually. It is characterized by complicated equations that are typically impossible to solve analytically, but even difficult to solve numerically. And we have developed a code that by the way, my intentions when I developed it, it was made in such a way that hopefully anybody interested in screening could modify it easily for their own problems. This is how I developed it. Whether I succeeded or not, it's up to the users to tell. But we did it to get the full numerical solutions of those and others, theory of screening. And we especially put a lot of effort onto these higher order operators. And we compared a theory of massive Galileans against a potential UV completion to see if screening was surviving the extension, and it didn't, which means it's unclear that Weinstein screening can be invoked within the limits of validities of the theories that make use of it. Where is the limit? The limit is that it could still be possible that for the slammed theories, a different UV completion is possible, which actually screens, but then I would say the burden of the proof is on someone to produce such a theory and show that it screens. Not so much produce such a theory, but show that it screens. And with this, I conclude. Thank you for your attention.